everything goes in quantum gravity or string theory. And indeed, the purpose of the swampland program is to distinguish between effective theories, which can be completed into quantum gravity in the high energy regime, from those which cannot. The former will be in the landscape of effective theories, while the latter will be in the swampland. The ideal approach would be then to really start from full string theory or M theory and just compute the desired low energy effective theory. But this is not feasible at present, essentially because we don't understand completely string theory in all of its details. So at present, the approach which is followed is a bit different. One can look at usually few known examples of trustable string theory constructions and then try to guess general properties out of this. And in particular, then one has to formulate out of these general properties some conjectures which have to capture fundamental properties of quantum gravity. And this conjecture usually has to be strongly tested in the sense that in the literature, there should be almost no known counterexample. So what I'm saying is that we are not really able to give a shape to the landscape, but what we are doing at present is that we are excluding parts of the swampland by means of conjectures. So this means that the best picture we have at present of the swampland program is in fact a work in progress list of conjectures. Some of them are believed to be robust, are strongly believed to be true, in fact, while some other are a bit more speculative at present. And in this talk, I will concentrate on three specific conjectures, which are the one I'm showing here in red. So I will talk about the Sitter conjecture, the Transplackian censorship conjecture, and the distance conjecture. So now I will first review briefly these three conjectures, and then in the second part I will show in which sense we made progress in the three of them. So the De Sitter conjecture essentially states in one line that any consistent effective theory consistent with quantum gravity should not emit De Sitter vacuum. And actually there is a precise formula proposed in the original paper, which is saying that the gradient of the scalar potential of this effective theory should be bounded by the actual value of the scalar potential itself, modulo some order 1 parameter C, which is set to be positive, but not specified otherwise, and this will be the topic in the second part of the talk. The motivation for this conjecture is essentially that at present, we don't have a clear example of the Sitter vacuum from string theory, so an example which is universally believed to be consistent in the whole community. The best proposals in this sense are KKLT and large volume scenarios, perhaps, but these are using ingredients which are not universally understood in this, for example, non-perturbative effects. On the contrary, what we do know is that we are able to prove in some situations, so under assumptions, that the conjecture is somehow theorem, in the sense that we have no-go theorems against classical De Sitter. In fact, we have a very long list of them, which I'm not reporting just for reasons of time and space. And also to be complete, I should also mention that the conjecture, the original conjecture, was refined in a series of subsequent papers. And now the motivation are essentially two. The differences are essentially two. First of all, the refinement now allows for local maxima. And second, in this refinement, the conjecture is somehow rephrased in some asymptotic regions, and I will talk more about these asymptotic regions later on. The second conjecture, which is important in this talk, is the Transplackian censorship conjecture. The statement of this conjecture says that sub-Planckian quantum fluctuation should always remain quantum and never become larger than the Albor horizon and then freeze and become classical. This conjecture is in fact motivated by a physical principle which has been also criticized recently. I'm just reporting one of the papers, one of the recent papers in this direction. But what is important in this talk is not really the original statement, but the consequences of this statement when you apply it to a theory, again, with scalar fields and the scalar potential. In fact, already in the original paper, a formula is proposed for a bound on the scalar potential of a given effective theory, which is the last formula I'm showing here in the slide. So this formula is similar to the De Sitter conjecture with two differences. First of all, there is an average, as you can see, and then some infinite field displacement is taken. So here we are probing somehow again the asymptotic regions, and then there is no free parameter actually. So the only number which appears is completely fixed by the space-time dimensions, and in d equal 4, this number is square root of 2 over 3. And in this talk, I will only concentrate on d equal 4, so or 4 non-compact space-time dimensions. The third conjecture I'm going to review, and which is important in this talk, is the distance conjecture. This conjecture is a bit older than the previous one, and also a bit more abstract. Again, this conjecture is applied to theories, to effective theories with scalar fields. So when you have a theory, an effective theory with scalar fields, then these scalars are somehow parameterizing the coordinates of some internal manifold. And then you can ask your effective theory what happens when you try to probe infinite distances or very, very large distances in this scalar manifold. Well, this conjecture is essentially saying that you should not ask this question to your effective theory because the effective theory is not valid in this regime. And the reason is very specific, and it is the fact that there is an infinite tower of states which have a mass which is exponentially suppressed with the distance delta phi. So when I'm sending delta phi to infinite, so when I'm probing infinite distances, then the mass of this tower of states, this infinite tower of states, become exponentially light. And again, you see that there is a parameter, which similarly to the De Sitter conjecture is not specified further. It is just postulated to be order 1 and positive. Well, then this means that when I'm probing infinite distances, then what I'm seeing is that there is an infinite number of new light degrees of freedom which try to enter the effective theory. But then this means that I have to reformulate from scratch my effective theory, or in other words, the original formulation of the effective theory breaks down. So to summarize the first part, we have three conjectures which are formulated in some asymptotic limit. We have the De Sitter conjecture, which is actually excluding the De Sitter vacuum. Then we have the distance conjecture, and these two conjectures have unspecified order 1 parameter C and lambda. And also there is a third conjecture, which is similar to the De Sitter conjecture, so the Transplackian censorship conjecture, but has no free parameter actually. There is a precise number which is predicted. So some general comments before going to the second part. For sure, the presence of conjecture is not satisfactory because eventually we would like to have mathematically proved the results. But still, I think that conjectures at the present stage are really helpful because they are suggesting possible directions in which to look first when we are investigating string theory. So string theory is a vast framework, and it is helpful to have hints on where to look first in order to find new and interesting results. The second comment, which is important in this talk, is that conjectures are not really just a list of unrelated points. So the list I was showing you before, the points in that list are not really completely unrelated. Instead, we know we have several examples of relationships that have been found among these points. So relationship among these conjectures. So in this sense, we talk about a web of conjectures. And in this talk, I will propose three different directions in which to make progress. Probably the easy one is to test existing conjectures. And indeed, I will show how we tested the conjecture I reviewed before in specific examples. And in particular, these conjectures were involving parameters. So one thing you would like to do is try to say something specific about those parameters. And I will show suggestions that these parameters should be bounded. Then the second step, which is a bit more difficult, is to relate conjectures. So build this idea of a web of conjecture. And again, referring to the previous point, in case you found possible bounds for parameters, then a natural question is whether or not these bounds are related. And finally, the most challenging is actually to propose new conjectures, which are trying to capture new properties, new unknown properties of quantum gravity. And in the last part, I will comment also on this very briefly. So let's start by testing and bounding. So in this paper with the people in Vienna, we looked at the Sitter conjecture first. And we test the de Sitter conjecture in a very specific framework. So we consider type 2 supergravity with sources and compactify from 10 dimensions to 4 dimensions on a group manifold, a generic group manifold. The reason why we choose the framework is because this framework is believed to be, in this framework, it is believed that you can possibly end up with what are called classical string backgrounds. So backgrounds in which you are able to reach a regime of large volume and weak coupling. And in this framework, we consider two sets of four-dimensional scalars, which you can think of as fluctuation of background quantities. So the first set contains three scalars, which have already been considered in the literature: rho, tau, and sigma. Rho can be understood as some fluctuation of the overall volume of the internal space. Tau is related to the dilaton, and there is also a power of rho entering the definition just for going to Einstein framing for dimensions. And sigma is similar to rho, again, is parameterizing some volume, but now this is the volume of the cycle, which is wrapped by the sources. The second set of scalars is a bit simpler. We have only two of them, r and tau. Again, tau is related to dilaton, while r is similar to rho, but it's a bit different also. So rho was the fluctuation of the overall volume, while now we are considering fluctuations along just one internal directions, because we wanted to understand what happens when you just fluctuate one of the direction and you freeze all the rest. And without loss of generality, you can just turn your reference frame and align it in such a way that the fluctuated direction is the first one. Now we have two different sets of scalars. It means that when you do the dimensional reduction, you will find two different scalar potential. The first one with the three scalars was already known, while the second one is a new result that we produced in the paper. So now that we have these two functions of the scalar fields, what we have done is that we consider linear combinations of the scalar potential and of the partial derivatives. And then, since we had in mind to test the de Sitter conjectures, under assumptions, we were able to write down inequalities of the type I'm showing here. And these inequalities, in fact, excluding the Sitter vacuum. The assumptions are needed in order to have zero on the right-hand side, because otherwise there will be something which is not vanishing. And A and BI are just numbers which are known explicitly once you do the computation. So once you are here, it is easy to recognize that this inequality is very similar, in fact, to the de Sitter conjecture. And in fact, once you are here and you know what A and BI are, then it is almost straightforward to read off the parameter C in the de Sitter conjecture, which is given by this combination of the parameters A and BI. So what we have done is in fact that we produced 10 different no-go theorems against Sitter, and we calculated the associated values of C. So we have 10 different values of C. And a priori, before doing the computation, we were generically expecting generic, in fact, order 1 numbers. We didn't see any reason why to see some pattern in these values. But this is not what we find. What we find is instead that all the values that we calculated are satisfying some bound, which is the one I'm showing here. C has to be bigger than square root of 2/3, and actually we find several cases of saturation. And surprisingly, this bound is precisely the number which is predicted by the TCC conjecture. So already at this stage, there is the question whether or not this is just a coincidence, or if it can be explained with some deeper idea related to the existence of a web of conjectures. Then the other conjecture we looked at and we tried to test is the distance conjecture. And again, there is a parameter here, lambda, which can be calculated in well-defined setups. Now, the logic to calculate lambda is essentially to relate the mass in the distance conjecture to some geometric quantity. And in this step, you usually use supersymmetry, because supersymmetry is giving you extra tools to do computations. There is a small caveat, which is the fact that the procedure actually is state dependent, because you expect the mass to be a different function depending on which kind of state you are considering. And in fact, in the literature, two kinds of states have been considered, we have BPS states, D-branes, for example, in n equal to compactifications on a Calabi-Yau, and in this case, the mass is equal to the central charge. So you know how to express the central charge, and then you read off the mass. The other kind of states, which have been studied, are Kaluza-Klein states, where the mass is given roughly by the inverse of the size of the compact dimensions. So what we have done in this setup is, first of all, we look at the literature and we collected all the known results of lambda we were able to find, and these are 19 different values for lambda. And then actually we calculated 3 new values for KK states. All of these values, so both PPS and KK states, satisfy again a bound, which is the following. Lambda is bigger than 1/2 square root of 2/3. And again, we find several cases of saturation. So the situation is similar to the previous one. A priori, we were expecting generic order 1 numbers, but this is not what we find. And interestingly, the same bound, in fact, has been proved independently in this nice paper, which appeared a few weeks later, and in which the authors show that this bound is in fact exact, is proven for a specific kind of state. So for BPS states on Calabi-Yau compactification, and it is also related to the weak gravity conjecture. Now, this is the first step, the easy one, in which you test conjectures and you find some results. Then the second step was to relate conjectures and then also to relate the bounds. So just to summarize, the results of the previous step is that a priori we were expecting generic order 1 numbers, but this is not what we find. And in fact, we find a simple relationship between the bounds that we are finding. So lambda and C are bounded by some values, lambda 0 and C0, which satisfy a very simple relationship. So 2 lambda 0 is equal to C0. So the distance conjecture is related to the de Sitter conjecture, and in turn, both of them are given by the same number predicted by the TCC conjecture in D=4. Now, the next step would be to relate conjectures. So you would like to relate the distance conjecture to the de Sitter conjecture, so the mass to the scalar potential. So naively, you would relate the mass to the second derivatives of the scalar potential, but this is not what you should do, because the mass in the distance conjecture is actually the mass of some external states, which is not inside your effective theory. Rather, what has been proposed to do in this series of papers is to relate the mass to the scalar potential itself. So the proposed relation, which we also are proposing, is something of this type. The mass should be related to some power of the scalar potential, and both should have an exponentially behavior in some asymptotic region. And there is a parameter alpha, which a priori should be some order 1 parameter. Now, to fix this parameter, let me do the third step. So the proposals. First of all, we would like to explain why we are finding some bounds on the distance conjecture parameter. Then one possibility that we propose is some generalized distance conjecture. So what we are proposing is the following. The mass of the states should not really have precisely the same behavior as an exponential suppressed with the distance, but should be bounded by an exponential suppressed with the distance. So what we are saying is that the mass can have in principle any possible functional form, but this generic functional form should be bounded by some exponential when I'm looking at asymptotic regions. The reason why we are doing this is essentially because if you repeat similar steps as in the TCC paper, then you actually are able to derive precisely the bound that we find. But let me stress that we lack, at this stage, a physical reason behind this. So this is certainly an open question still, something we have still to investigate. The second proposal comes back to the previous proposed relations among conjectures. So we are proposing the existence of some correspondence between conjectures, in the sense that every time in a system there is some mass which is satisfying the distance conjecture, then there should exist another system in which the scalar potential V satisfies the de Sitter conjecture. And now, thanks to our results, we are able to fix this alpha to be precisely 1/2. And parallel to this, we in fact also verified that every time we were taking our scalar potential, so the two functions of the scalar fields we calculated, then these in principle are complicated functions, but every time we were looking in asymptotic regions, then we were always finding some exponential. So to conclude, the motivation for these kind of studies is essentially to understand some general properties of quantum gravity and string theory. And as I was saying, at the previous stage, conjectures are the starting point of a quantitative analysis. And then in this general framework, we propose three different directions in which to improve our understanding of the swampland problem. In the first case, we essentially checked non-trivially two conjectures in a huge class of examples. And also we found evidence that the parameters entered in the conjecture should be bounded. Second, we studied relations among conjectures, and also we studied relations among the bounds that we found in the previous step. And finally, we proposed some generalization of conjectures in order to explain our result, but certainly this last part, is the more speculative. So open questions, possible open questions. For example, one can ask what happens in dimensions different than 4. So all of our results were produced in 4 dimensions. Then a natural question would be to try to extend the analysis to other dimensions. In this case, we need examples because most of the examples we have are in fact for 4 dimensions. And finally, what I think is one of the big open questions is what is the physical reason why we are seeing all of these relationships among conjectures. So what is the physical motivation, the physical principle underlying the existence of the web of conjectures? Thanks.
Great. Thank you, Niccolò. Are there any questions? Yeah, let's all clap with our reaction Zoom thing. Irena has a question.
Hi. Yes.
Hi.
Thanks for the talk, Niccolò. Yeah, I have some questions about your proposals, in fact. I mean, could you come back to the slide? Yes, here. Yeah, so I have 2 questions. First, when you say that the mass has to be bounded this way, are you thinking of the same tower along the geodesic, that the mass always has to satisfy this exponential rate with bounded by this lambda 0, or not?
I'm not sure I understand. So what we are seeing...
Always the same tower. I mean, given if you fix some tower that is becoming light along some geodesic, is always the same tower that has to become light.
Okay, I think we didn't ask ourselves this question, so I'm not sure precisely. What I'm saying is just the mass we are seeing can have any functional form, which has to be bounded in this way.
Okay. No, just because if it's the same tower all the time, then we have counterexample for that. But
okay.
if you allow to have different towers at every point in field space.
Okay, I think we didn't put that assumption in fact.
Okay, that's good to know. And then also the other question I have, when you have the proposal too.
Yes.
And you say that you have to relate these 2 setups. I mean, that there are always 2 setups, no, in which the exponential.
Well, what we find in our example is that we have 2 different setups. Yes.
But how do you choose what setups? I mean, is there any relation between them? I mean, how?
This is an open question. In the setups we look at are completely independent a priori. For example, the distance conjecture used supersymmetry, while in the setups we looked for the de Sitter conjecture, we didn't use supersymmetry at all. So these setups are completely independent, but we always found some pairing in this way.
But is there any physical intuition of how to select
not yet.
to hook up?
No, not yet, I would say.
Because I mean, I can see a geometric reason, because precisely the setup you are taking, even if we change the level of supersymmetry, add fluxes and so on, the geometry sometimes is the same. So the numbers are the same, but yeah, I would like to understand if there is some physical.
Yes, this is an open question, in fact. This is why I was writing speculative, because this is just some tentative explanation we are trying to do in the very last part of the analysis, but these are still open questions.
Okay, thank you.
Thanks.
Tom?
Hi. Yeah. So on the same slide, I was wondering, how is the TCC giving this bound here on the derivative of the mass? Because my understanding is the TCC is a condition on the potential. Are you somehow relating the potential to this mass?
Somehow, yes. And then you have just to calculate this average as it is defined in the TCC, and you find essentially the same steps. So there are corrections which are suppressed with 1 over delta phi. And then if you send delta phi to infinity, you get just precisely the very first term.
But I'm wondering how you're relating the mass here to the Transplackian nature of the modes.
No, we don't have a physical principle, if this is what you're asking. It's just a technical trick.
Okay, can you explain this technical trick, or at least outline it?
Well, I mean, if you just consider this thing, you are somehow extracting the lambda from the exponential. It's just purely technical thing.
I understand that this derivative here will allow me to extract this lambda. I'm wondering how the TCC is placing a bound on this quantity, though.
Well, the reason why I wrote TCC is because it's similar, but you should not compare this to the TCC. If this is your question. So this is not, I'm not relating this to the TCC at all. The TCC has a physical reason underlined. This has not, at least at present.
But I thought you're saying that the TCC implies this bound here.
No. If you follow similar steps, if you do similar calculations as in the TCC.
Okay.
But I'm not saying that TCC is implying this. This is just one thing we came up with in order to explain the bound on lambda. But there's not physical reason as in TCC.
I see. Okay, thank you.
Thanks.
Great. Let's take 2 more questions. Jonathan?
Have you looked at what happens under higher derivative corrections? In particular, what happens to these bounds? Do they get sharper or weaker?
No, we didn't look at this. We just considered 2 derivatives Lagrangians.
Well, but you also relate this to, you mentioned that it's related to possibly other swampland conjectures, and their derivatives have been considered in some cases.
Sorry, I mentioned that is related to?
Other swampland, so the whole point, right, is that all these things are interconnected, and so
Yes.
But higher derivative corrections have been considered in some of these other conjectures.
No, we didn't look into this.
Okay, thanks.
Thanks.
And David?
Yes, I just wanted to comment further, as Niccolò did, to come back to a question to Irene on the correspondence. And as Niccolò said, the setups are very different. On one side, there's supersymmetry, and on the other one, there's not. And also, the setups are different because the compactification manifolds are very different. On one hand, there's a Calabi-Yau, on the other hand, it's a group manifold. And so one physical intuition behind this would be some sort of duality, like a T-duality or something like this, to relate to very different compactification setups. And we have one paragraph saying with the word duality and arguing in this direction, just to complete the answer. And to answer to Jonathan, it would be interesting to look at higher derivative corrections. And one reason for the inequality on the generalized distance conjecture is indeed to allow for quantum corrections, because there were some discussions, for instance, in the paper by Blumenhagen and collaborators, which was allowing for quantum corrections like log corrections. And maybe this is the type of thing that you could put within such an inequality. So maybe this goes in the direction that you're thinking about. On the other hand, these proposals are valid in asymptotic limits. So maybe once you start including corrections, things start breaking down, actually.
Yeah, they probably break down, but the question is, what direction does the first correction push it? Does it strengthen it or weaken it? I mean, presumably it weakens it, but
yeah, it would be interesting to look at this more precisely, yes.
Oh, great. Let's thank Niccolò again for his very nice talk.
Thanks.
And then